My name is Juanisa de Jesus Briones Herrera. I am a student at the Division of Science and Engineering at the University of Guanajuato, and today I will present my research entitled Solvothermal Cobaltum, Neodymium, Indium, Yttrium, Lanthanum sulfide catalysis for superior hydrogen evolution in acid and alkaline media. The production of green hydrogen has become one of the key strategies to move towards sustainable energy system. Hydrogen is an attractive fuel because it has a high energy density and it's only byproduct when used its water, making it environmentally clean. However, one of the bottlenecks in large-scale hydrogen production is the hydrogen evolution reaction, or HER. This reaction is typically catalyzed by platinum-based materials, which are highly efficient but also extremely expensive and scarce. Because of this, a central challenge in material science is to design alternative catalysts that are efficient, stable, and cost-effective. This is where high-entropy materials come into play. High-entropy compounds are built from 5 or more elements mixed in near equimolar ratios. This multi-element approach produces a high configurational entropy, which helps stabilize complex solid solutions and results in unique electronic and structural properties not observed in simpler systems. In the case of sulfides, these materials can offer both conductivity and catalytic activity, making them promising candidates for HER. In this project, we focus on synthesizing a high-entropy sulfide catalyst with the composition for cobaltum, neodymium, indium, yttrium, and lanthanum. The synthesis was carried out using a solvothermal method, which is advantageous because it allows to control reaction temperature, time, and solvent environment to tune the morphology and crystallinity of our product. Once the material was obtained, we performed X-ray diffraction to analyze the crystalline phases and structural order, electrochemical characterization, including the next linear sweep voltammetry to measure of potential and catalytic activity, electrochemical impedance spectroscopy to assess charge transfer resistance, a stability test to evaluate performance over time and under cycling. This combination of structural and electrochemical characterization provided a completed picture of how the material behaves as an electrocatalyst. Now, let me highlight the main results. Structural results. The X-ray patterns confirm the formation of crystalline sulfide phases. At lower synthesis temperatures, the patterns showed considerable noise, suggesting poor crystallinity. However, when increasing the solvothermal treatment temperature, the diffraction peaks became sharper and more defined, indicating a clear improvement in crystallinity. This means that fine-tuning synthesis parameter has a direct effect on structural equality. 2. Electrochemical performance. In linear sweep voltammetry, the catalyst demonstrated competitive overpotentials to reach the benchmark current density of 10 milliamperes per square centimeter. Compared with several reported sulfides, our high-entropy sulfide showed superior activity, placing it among the promising alternatives to noble metals. Electrochemical impedance spectroscopy revealed low charge transfer resistance, which indicates that the material facilitates efficient electron transport during the reaction. Interestingly, the material showed higher current density and slower scan rates. This behavior suggests that the intrinsic catalytic activity is strong, and that slower scans allow for better utilization of the active sites. 3. Stability results. A stability test showed that the material was able to maintain its catalytic activity during extended electrochemical cycling. While more long-term tests are needed, the preliminary results are encouraging, showing that the catalyst does not degrade significantly under reaction conditions. To put this into context, the platinum still remains the best performing catalyst for HER. However, its cost and scarcity makes it impractical for widespread hydrogen production. Among transition metal sulfides, many reported systems show moderate activity but often lack stability. Our high-entropy sulfide catalysts outperform several of these reported systems, both in terms of overpotential and in stability. The improvement in activity can be attributed to the synergistic effects of multiple elements in the high-entropy design. The combination of cobalt, neodymium, indium, yttrium, and lanthanum likely introduce a variety of local electronic environments, which enhances catalytic activity. Moreover, the multi-element structure could provide greater tolerance to degradation, explaining the observed stability. From these results, we can draw several key conclusions. 1. The solvothermal synthesis route is effective for producing high-entropy sulfides, although optimizing temperature and other parameters is crucial for achieving good crystallinity. 2. Synthesized cobaltum, neodymium, indium, yttrium lanthanum sulfide catalysts demonstrate competitive catalytic performance for HER, surpassing many previously reported sulfide systems. The catalyst shows promising stability and improved activity at slower count rates, indicating good potential for practical application. For future work will focus on optimizing synthesis conditions, performing more extensive long-term stability tests, and explore other high-entropy compositions to tailor performance for different electrolytic environments. Acknowledgements. I would like to sincerely thank my advisors, Dr. Cristian Gómez Solís y José Noé Zavala Collar, for the guidance and support throughout this project. I also acknowledge the University of Guanajuato and the Centro de Investigaciones en Óptica for providing the resources and laboratory facilities that made this work possible. Thank you very much for your attention, and I will be happy to answer all your questions.